Welcome to The Chill Scientist. This is part 3 of black holes. Check out parts 1 and 2 to understand this much better. Let's jump right in. Once formed, early black holes acted as gravitational magnets, pulling in nearby gas and stars, and eventually settling into the centers of forming galaxies. As they accreted material, they emitted tremendous amounts of radiation that influenced their surroundings, heating and ionizing the intergalactic medium. Quasars, therefore, played a crucial role in a major phase of cosmic evolution called reionization, the period when ultraviolet light from the first stars in black holes stripped electrons from neutral hydrogen atoms, making the universe transparent to light. The structure of a quasar is complex, but well understood in broad terms. At its heart lies the supermassive black hole, surrounded by an accretion disk of infalling gas and dust heated to millions of degrees. Above and below this disk lie regions of high-speed clouds that emit broad spectral lines as they move at thousands of kilometers per second. Farther out, cooler clouds produce narrower lines. Surrounding all of this is a dusty torus, a donut-shaped ring that absorbs some of the radiation and re-emits it in the infrared. When the orientation of this structure aligns so that we can see directly into the disk and broadline regions, we observe a quasar. When our view is obscured by the torus, we see a less luminous but still active nucleus known as a Seyfert galaxy or radio galaxy, depending on its other characteristics. This model, known as the unified model of active galactic nuclei, explains why such diverse objects appear to share the same underlying engine, the accretion of matter onto a supermassive black hole. Many quasars also produce relativistic jets, narrow beams of charged particles accelerated to near the speed of light by magnetic fields. These jets can extend for millions of light years and emit strongly in radio wavelengths. When one of these jets is pointed directly toward Earth, the source is observed as a blazar, a class of AGN known for violent variability and high-energy emissions. Blazars are among the brightest continuous sources in the gamma-ray sky. Over cosmic time, quasars have become less common. The peak of quasar activity occurred around 10 billion years ago, during the epoch when galaxies were most actively forming stars. Since then, as galaxies exhausted their gas supplies or stabilized under feedback from their central black holes, the most powerful quasars have faded. Today, most supermassive black holes, including Sagittarius A star at the center of the Milky Way, are dormant or only weakly active, accreting matter at very low rates. Still, the remnants of their active pasts remain immense. The jets, winds, and radiation they once produced have left imprints in the surrounding medium, influencing the temperature and structure of intergalactic space. In many ways, quasars served as the engines that reheated and reshaped the young universe, dispersing heavy elements and regulating the pace of cosmic evolution. Even in their quiet phases, supermassive black holes continue to shape their galaxies. Their gravitational presence stabilizes galactic centers, influences star orbits, and helps maintain the overall structure of spiral arms and bulges. Some researchers speculate that without them, galaxies might not form stable, long-term configurations at all. In essence, quasars represent the universe at its most extreme, both in energy output and in physical conditions. They show us what happens when the most fundamental forces of nature operate at their limits. And through them, we can trace the growth of black holes from the dawn of time to the modern cosmic landscape, linking the smallest scales of physics to the largest structures in existence. The discovery of gravitational waves revolutionized astrophysics by giving us an entirely new way to observe black holes. Until recently, everything we knew about the universe came from light. Electromagnetic radiation across the spectrum, from radio to gamma rays. But black holes, by their very nature, absorb light rather than emit it, revealing themselves only indirectly through the behavior of nearby matter. Gravitational waves, on the other hand, carry information directly from the motion of massive objects, unaffected by dust, gas, or opacity. They are ripples in space-time itself, generated when immense masses accelerate, particularly during events like the collision and merger of black holes. Einstein predicted gravitational waves in 1916 as a consequence of his general theory of relativity. According to the theory, when a massive object moves, it distorts space-time, and changes in that distortion propagate outward at the speed of light. For most objects, even large stars or planets, the effect is extraordinarily small, far below what could ever be measured. But when two black holes spiral toward each other and merge, the energy released in gravitational waves can exceed the combined light output of every star in the observable universe, albeit for only a brief moment. Detecting such waves required technology capable of measuring changes in distance smaller than a fraction of the width of a proton. This challenge was met by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States. LIGO consists of two detectors, one in Washington state and the other in Louisiana, each with two perpendicular arms, 4 kilometers, 2.5 miles long. Laser beams travel down these arms, bounce off mirrors, and recombine. If a gravitational wave passes through, it stretches one arm while compressing the other, changing the interference pattern of the laser light. For decades, LIGO detected nothing, until September 14, 2015, when a clear signal arrived almost simultaneously at both detectors. The waveform matched exactly what relativity predicted for the merger of two black holes, each roughly 30 times the mass of the Sun, located about 1.3 billion light-years away. The event, named GW 150914, lasted just a fraction of a second but confirmed that gravitational waves were real and that black hole binaries existed. It was one of the most important discoveries in modern science, earning the 2017 Nobel Prize in Physics. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, most from merging black holes and some from neutron star collisions. Each detection provides new insight into the population, distribution, and properties of compact objects in the universe. By analyzing the shape and timing of the waveforms, scientists can determine the masses, spins, and even approximate distances of the merging bodies. One of the most striking findings from these detections is the diversity of black hole masses. Before LIGO, most known stellar black holes had masses around 5 to 15 times that of the Sun, inferred from X-ray binaries. But gravitational wave detections revealed black holes far heavier, up to 80 solar masses or more. This suggests that the processes forming black holes in massive stars, particularly in low metallicity environments where stars lose less mass to stellar winds, may be capable of producing much larger remnants than previously thought. The mergers themselves also tell us about how black hole binaries form. Some pairs likely originate from binary star systems that evolve together and collapse in sequence, remaining gravitationally bound. Others may form dynamically in dense stellar environments, such as globular clusters, where random encounters can bring two black holes together. The distribution of spins, orbital orientations, and merger rates helps astrophysicists distinguish between these formation channels. Beyond astrophysics, gravitational wave detections serve as precision tests of general relativity. Every observed waveform so far matches Einstein's predictions to extraordinary accuracy. No deviations, such as those that would hint at new physics or modifications to gravity, have been detected. But researchers continue to push for higher precision and new frequency ranges, hoping that one day an unexpected signal might reveal a deeper layer of reality. Another remarkable event came on August 17, 2017, when LIGO and Virgo detected GW 170817, the merger of two neutron stars rather than black holes. For the first time, the gravitational wave signal was accompanied by electromagnetic radiation, gamma rays, visible light, and radio waves observed by dozens of telescopes worldwide. This multi-messenger detection confirmed that such collisions produce heavy elements like gold and platinum, showing how these rare materials are forged in the universe. Though not a black hole merger initially, the event ended with the formation of a black hole, completing the cycle of matter and gravity in a single observable event. Future detectors will expand this new form of astronomy even further. Projects such as LISA, Laser Interferometer Space Antenna, planned for launch in the 2030s, will place 3 spacecraft in orbit around the Sun, millions of kilometers apart. Unlike ground-based detectors, LISA will be sensitive to lower frequency waves produced by supermassive black holes merging or interacting. This will allow scientists to observe the growth of black holes across cosmic time, from early quasars to modern galactic centers. Other proposed observatories, such as the Einstein Telescope in Europe and Cosmic Explorer in the United States, aim to increase sensitivity by an order of magnitude. With these tools, astronomers expect to detect thousands of events per year, mapping the black hole population throughout the observable universe. In addition, pulsar timing arrays, networks of millisecond pulsars monitored for tiny variations in their signals, have begun detecting evidence of a stochastic gravitational wave background. This background likely arises from the slow, large-scale spirals of supermassive black hole binaries over billions of years. If confirmed, it would represent the collective hum of countless distant mergers, providing a direct probe of how galaxies and black holes have grown together over cosmic history. Gravitational waves have turned what was once a purely theoretical aspect of relativity into a practical observational science. They offer a way to study the universe's most violent and hidden phenomena: black holes colliding, neutron stars collapsing, space-time ringing like a bell. Each detection is a direct recording of the movement of mass itself, unfiltered by light, matter, or distance. And perhaps most importantly, this new window into the cosmos is still in its infancy. As detectors grow more sensitive and cover wider frequency ranges, they will reveal events we have not yet imagined, perhaps even collisions involving exotic objects that challenge our understanding of physics. Black holes, once symbols of invisibility, are now among the loudest voices in the cosmic symphony. When matter crosses the event horizon of a black hole, it disappears from the observable universe. From the outside, it seems as if it's simply gone, absorbed into an infinitely dense point from which not even light can escape. But what actually happens to that matter inside the black hole remains one of the deepest and most unsettled questions in physics. According to Einstein's general theory of relativity, once matter passes the event horizon, it inevitably continues inward, drawn by gravity toward a region known as the singularity. In this region, density and space-time curvature become infinite, and the known laws of physics break down. Relativity can describe how matter falls in, but not what occurs once it reaches that final destination. Infinity is not a physical quantity. It's a sign that the theory itself has reached its limits. In a non-rotating, uncharged black hole, the simplest kind, described by the Schwarzschild solution, the singularity is a single point at the center. For a rotating black hole, described by the Kerr solution, the structure is more complex. The singularity becomes a ring, and the interior space-time includes multiple regions separated by hypothetical inner horizons. In mathematical terms, these regions could connect to other universes or distant parts of our own, forming what's known as a wormhole. However, these solutions are unstable. Any disturbance, such as infalling matter or radiation, would likely cause the wormhole to collapse. Physically, it's not clear that a singularity, as predicted by relativity, truly exists. Most physicists believe that a complete theory of quantum gravity, one that unifies general relativity with quantum mechanics, would remove the infinities and replace the singularity with something finite but extreme. This remains one of the most important open problems in theoretical physics. One of the major difficulties is that relativity and quantum mechanics operate under entirely different rules. Relativity describes space-time as continuous and smooth, while quantum theory deals with discrete probabilities and uncertainty. When the two come together in a region of immense gravity and tiny scale, like the core of a black hole, their equations conflict. Several competing ideas attempt to resolve this. In loop quantum gravity, space-time itself is quantized, made of tiny, discrete loops rather than a continuous fabric. In this framework, the singularity might be replaced by a dense core, where quantum effects create a repulsive force that prevents infinite collapse. This could even allow for a bounce, wherein falling matter re-expands in some form, potentially linking to another region of space-time. String theory offers another possibility. It replaces point-like particles with one-dimensional strings whose vibrations determine their properties. At extremely high energies, strings could spread out gravitational effects, preventing the formation of an infinitely small singularity. Some string theory models suggest that the interior of a black hole might transition into a different type of object entirely, sometimes described as a fuzzball, a tangled mass of strings and brains with no sharp boundary. What happens to information inside a black hole is another profound puzzle. In quantum mechanics, information, meaning the physical details about a system's initial state, cannot be destroyed. But when something falls into a black hole, all observable information about it seems lost, except for the black hole's total mass, spin, and charge. This contradiction between quantum theory and general relativity is known as the black hole information paradox. Stephen Hawking was among the first to explore this paradox seriously. In 1974, he demonstrated that black holes are not entirely black. Through a process now called Hawking radiation, quantum effects near the event horizon allow particle-antiparticle pairs to form. One particle escapes as radiation while the other falls in, reducing the black hole's mass slightly. Over time, this process causes black holes to slowly evaporate. For stellar mass black holes, the evaporation time is far longer than the age of the universe, on the order of 10 to the power of 66 years. But for small black holes, it could be much shorter. Hawking's discovery linked gravity, quantum mechanics, and thermodynamics in a profound way. It showed that black holes have a temperature proportional to their surface gravity and an entropy proportional to their surface area, not their volume. This insight led to the idea of the holographic principle, proposed by physicist Gerard T. Hooft and developed by Leonard Susskind. It suggests that all the information about the three-dimensional contents of a region of space can be encoded on its two-dimensional boundary, just as a hologram encodes a 3D image on a flat surface. Applied to black holes, the holographic principle implies that the information about everything that has fallen in might somehow be stored on the event horizon itself. This would mean that information is not truly lost, but rather transformed and preserved in a highly scrambled form. When the black hole eventually evaporates, that information could, in theory, be released again through subtle correlations in the emitted radiation. Still, the precise mechanism for how this would happen remains unknown. Some theorists argue that black holes might leave behind remnants, small, stable objects that contain all the information from the original system. Others suggest that the event horizon is not a smooth boundary, but a chaotic, energetic layer called a firewall, where infalling matter is destroyed violently. The firewall idea, however, conflicts with the equivalence principle of relativity, which states that a freely falling observer should experience no special effects at the horizon. Experiments cannot yet probe what happens inside black holes directly, but indirect clues may emerge from observations of black hole mergers, Hawking radiation analogs in laboratory systems, or signatures of quantum gravity in cosmic data. Some researchers even speculate that microscopic black holes might be created in high-energy particle collisions, such as those at the Large Hadron Collider, although no evidence for this has been found. What's clear is that the interior of a black hole represents a boundary in our understanding of nature, a place where our best theories collide and neither fully succeeds. For over a century, black holes have served as testing grounds for the extremes of physics, and their interiors are the ultimate frontier of that exploration. They remind us that our universe still hides layers of structure we have yet to uncover. The solution to what lies inside them could reshape not only our understanding of gravity, but also of space, time, and reality itself. If left undisturbed for unimaginably long periods of time, black holes will eventually disappear. Despite their reputation as eternal cosmic prisons, they are not permanent features of the universe. The process that causes their demise, known as Hawking evaporation, is among the most striking predictions in theoretical physics. It reveals that even in the deepest gravitational wells, quantum mechanics still has a say. As Stephen Hawking showed in 1974, black holes emit radiation due to quantum fluctuations near the event horizon. Space is never truly empty. It constantly teems with short-lived particle-antiparticle pairs that appear and annihilate within fractions of a second. Ordinarily, these pairs cancel each other out, leaving no lasting effect. But near an event horizon, gravity can separate them. One particle falls into the black hole, while the other escapes to infinity. To an external observer, it appears as if the black hole is radiating energy. The escaping particle carries positive energy away from the system, while the infalling one effectively carries negative energy relative to the outside universe. The result is that the black hole loses a tiny amount of mass. Over vast timescales, this process accumulates, and the black hole slowly shrinks. The temperature of Hawking radiation is inversely proportional to the black hole's mass. This means that the more massive a black hole is, the colder it becomes. A black hole with the mass of the Sun would have a temperature of roughly 60 nanokelvins, far colder than the cosmic microwave background radiation, which is about 2.7 kelvins. In other words, stellar and supermassive black holes are currently absorbing more radiation from the universe than they emit. They will not begin to truly evaporate until the background temperature drops below their own. That won't happen anytime soon. In the current epoch, the universe is only about 13.8 billion years old. A solar mass black hole would take roughly 10 to the power of 66 years to evaporate completely, a number so vast it defies ordinary comprehension. For supermassive black holes, such as the one at the center of the Milky Way with about 4 million solar masses, the timescale stretches to around 10 to the power of 90 years. For comparison, a trillion years is only 10 to the power of 12. As a black hole radiates, it loses mass and becomes smaller, which makes it hotter. This creates a feedback loop. The smaller it gets, the faster it evaporates. Near the final stages, the radiation output would rise dramatically. A black hole the size of a mountain, weighing around 10 to the 11th kilograms, roughly 220 billion pounds, would radiate at thousands of degrees and evaporate in a burst of high-energy gamma rays. If primordial black holes formed in the early universe, tiny relics from density fluctuations, some could be finishing their evaporation right now, releasing detectable bursts. However, no such events have yet been observed. The end of black holes ties into the ultimate fate of the universe. As stars exhaust their nuclear fuel and galaxies grow dark, black holes will dominate the cosmic landscape. This is the era sometimes called the black hole era, predicted to begin roughly 10 to the 40 power years from now. By that time, most stars will have burned out or been ejected from galaxies, and the remaining matter will have either fallen into black holes or dispersed. During this epoch, black holes will slowly evaporate, one by one. The smaller ones will vanish first, followed by the supermassive ones. Their final evaporation will release the last significant bursts of energy in an otherwise cold and fading universe. By the time the largest black holes disappear, Trillions upon trillions of years into the future, the cosmos will be a thin sea of photons, neutrinos, and stray elementary particles drifting apart in near-perfect emptiness. This long, slow decline is sometimes called the heat death of the universe. It's the inevitable consequence of entropy, the gradual dispersal of energy until no organized structures or processes remain. In this distant future, all sources of usable energy will have been exhausted. Stars, galaxies, and eventually even black holes will be gone. The temperature everywhere will approach absolute zero. Some physicists have speculated that quantum effects might allow for new forms of structure to emerge even then. But according to current understanding, the universe will eventually become a silent, dark expanse. Time itself will lose meaning, as nothing changes and no clocks can tick. Yet black holes play a crucial role in driving this cosmic evolution. They are the ultimate engines of entropy, each one representing an enormous concentration of information and thermodynamic disorder. When they evaporate, they release that stored entropy back into the universe, accelerating its march toward equilibrium. It's also possible that black holes could contribute to entirely new universes. Some speculative cosmological models propose that the final stages of black hole evaporation might trigger quantum fluctuations large enough to create new regions of space-time, effectively baby universes branching off from ours. These models, though highly theoretical, suggest that black holes could serve not just as cosmic endpoints, but as seeds for future creation. What makes this idea appealing is its symmetry. Black holes collapse matter into nearly infinitesimal scales, while the Big Bang represents an expansion from such scales. The two processes mirror each other, one imploding, the other exploding, hinting at a deeper unity that we don't yet understand. If this is true, then every black hole might contain the birth of another universe, hidden behind its event horizon. Our own Big Bang could, in turn, have originated from the interior of a black hole in a parent cosmos. This remains speculative, but demonstrates how the study of black holes touches the deepest questions of existence: where the universe came from, what laws govern it, and whether creation and destruction are simply two sides of the same process. Even if these ideas remain beyond current proof, the physics of black holes continues to guide our exploration of the universe's destiny. They remind us that everything, even the most permanent-seeming objects, was temporary. In the end, gravity itself ensures that all things fade, leaving behind only the faint echo of energy and the geometry of space-time. Time behaves differently near a black hole than it does anywhere else in the universe. The immense gravity warps space-time so drastically that time itself slows down relative to regions farther away. This isn't just a mathematical abstraction, it's a physical reality predicted by general relativity and confirmed by experiment. The closer something gets to the event horizon, the more extreme this time dilation becomes, eventually reaching the point where, from an outside perspective, time appears to stop altogether. To understand why this happens, imagine space-time as a flexible grid that can stretch and curve in response to mass. A planet like Earth produces a small dent in that grid. A black hole, by contrast, produces such a steep curve that the grid effectively folds inward toward its center. Time and space, which normally run at right angles to each other, become mixed. Near the event horizon, the direction we think of as forward in time begins to tilt toward the black hole's center. Crossing the horizon, the inward direction of space and the forward direction of time effectively become the same. Once inside, motion toward the singularity isn't just inevitable, it's as unavoidable as moving into the future. For an external observer watching an object fall toward a black hole, this distortion creates an illusion. As the object approaches the event horizon, it appears to slow down, its light increasingly redshifted to longer wavelengths. Eventually, it seems frozen just outside the edge, fading from view as the light becomes too red and faint to detect. From the outside, the object never quite crosses the horizon. But from the falling object's own frame of reference, time passes normally. It crosses the event horizon in finite time and continues inward without noticing anything unusual at the boundary. This difference arises because time dilation is relative. Each observer experiences time at a normal rate locally, but those rates diverge drastically when strong gravitational fields are involved. Even the relatively weak gravity near Earth causes measurable effects. GPS satellites orbiting above the planet's surface experience slightly faster time than clocks on the ground, and their systems must compensate for this difference to remain accurate. Near a black hole, this effect becomes extreme. In theory, if you orbited just outside the event horizon of a supermassive black hole, you could experience only a few hours while billions of years passed in the outside universe. This idea, though dramatized in science fiction films, is consistent with relativity. Though surviving such proximity would require precise orbital conditions and protection from tidal forces. Tidal forces are another key effect of gravity near a black hole. They arise because the gravitational pull on one part of an object differs from the pull on another part. On Earth, they cause the ocean tides, with the side facing the moon experiencing a slightly stronger pull than the far side. Near a black hole, these gradients become deadly. For a stellar mass black hole, tidal forces near the event horizon are so intense that they would stretch an object lengthwise and compress it sideways, a process known as spaghettification. The difference in gravity between your head and your feet would be enough to tear you apart long before you reach the singularity. However, near a supermassive black hole, the event horizon is much farther from the central singularity, and the gradient is less severe. You could, in theory, cross the horizon without immediate destruction, though you would still be doomed to fall inward eventually. The experience of falling into a black hole would depend on its mass and rotation. For a non-rotating black hole, you would see the outside universe become increasingly blue-shifted as you approached, then fade into darkness as light paths curved inward. If the black hole were rotating, frame dragging would twist space-time around you, causing the stars to appear to spiral and distort. You might even see multiple images of the universe overlapping, light bending in complex arcs as it circled the black hole multiple times before reaching your eyes. From a purely physical standpoint, once you cross the event horizon, escape would be impossible. All paths through space-time, including those that light can follow, lead inevitably inward. There is no turning around or hovering in place. The singularity lies in your future just as tomorrow lies in the future on Earth. Yet from the outside, none of this would ever be visible. To an external observer, you would appear to freeze and fade at the horizon, while the black hole itself would absorb the energy and information of your info. In effect, two versions of you exist in two different reference frames, one falling smoothly inward and one eternally suspended on the edge of time. This paradox, that an object both crosses the horizon and never does, depending on perspective, is one of the subtler mysteries of relativity. It demonstrates how space-time is not a universal stage, but a flexible geometry that depends on where and how you observe it. Black holes, therefore, are not just gravitational traps. They are natural laboratories for the study of time itself. They show that time is not an absolute flow, but a local experience shaped by gravity. They reveal that the distinction between space and time is not fixed, but interchangeable under extreme conditions. In the far future, when black holes dominate the cosmos, these effects will determine how the last remnants of matter evolve. For anything falling into one, time and existence end together at the singularity. For distant observers, those same events stretch out endlessly, frozen on the boundary of space-time. It's a haunting symmetry. Inside, time ends. Outside, it slows forever. Black holes are where time itself unravels, the closest thing nature offers to a physical edge of reality. Black holes may seem like cosmic vacuums that simply swallow everything nearby. But in reality, They are among the most dynamic and energetic systems in the universe. When surrounded by gas, dust, or stellar debris, they can transform gravitational energy into light and motion on colossal scales. The space around an active black hole can glow brighter than an entire galaxy, driven by the physics of accretion, the process by which matter falls inward. Accretion disks form when infalling material carries angular momentum, meaning it has some sideways motion relative to the black hole. Instead of plunging directly in, the material spirals around, forming a thin, rapidly rotating disk. Friction within this disk, along with magnetic interactions, causes the gas to heat up to extraordinary temperatures. Near the inner edge, temperatures can reach tens of millions of degrees Celsius, or tens of millions of degrees Fahrenheit. At those levels, atoms are stripped of their electrons, and the disk emits high-energy X-rays and ultraviolet light. The efficiency of this process is remarkable. A black hole accretion disk can convert up to about 10% of the infalling mass into radiation, and for rapidly spinning black holes, as much as 40%. By comparison, nuclear fusion in stars converts less than 1% of mass into energy. This means that matter falling into a black hole produces more energy per unit mass than any other known mechanism in nature. These extreme environments are not chaotic in the ordinary sense. They follow precise physical laws, particularly those of magnetohydrodynamics, which describe how magnetic fields interact with hot, ionized gas or plasma. As the plasma orbits, magnetic fields become twisted and amplified, sometimes reconnecting explosively to release energy. These processes drive turbulence and can channel material into narrow, focused streams that escape along the black hole's rotational axis. These outflows, called relativistic jets, are among the most striking features of active black holes. Composed of charged particles accelerated to near the speed of light, jets can extend for thousands or even millions of light years, cutting through interstellar and intergalactic space. They radiate across the electromagnetic spectrum, from radio waves to gamma rays, and can outshine their host galaxies. Despite decades of study, the precise mechanism behind their formation is still debated, though magnetic fields anchored in the accretion disk and threading the black hole's spin are believed to play the central role. The leading theoretical framework for this process is the Blandford-Znayak mechanism, proposed in 1977. It describes how a rotating black hole can transfer energy from its spin to surrounding plasma via magnetic field lines. In essence, the black hole acts as a unipolar inductor, similar to a cosmic dynamo, powering the jets through pure rotation. This process can extract vast amounts of energy without requiring the black hole itself to lose mass directly. Jets profoundly affect their surroundings. When they slam into interstellar or intergalactic gas, they create massive shock waves that heat and compress the medium, sometimes triggering new star formation or, conversely, preventing it by expelling gas from galaxies. This feedback helps regulate galaxy growth. Observations show that the most massive galaxies, which host the largest black holes, tend to have lower star formation rates, likely because their central black hole's activity keeps surrounding gas too hot to collapse into new stars. Accretion disks also produce other distinctive features, such as coronae, regions of hot magnetized plasma hovering above the disk that emit high-energy X-rays. Variations in the brightness of these X-rays, observed over timescales of seconds to hours, reveal the structure and motion of matter just outside the event horizon. Some systems show quasi-periodic oscillations, rhythmic fluctuations that may reflect orbital motion near the inner edge of the disk, providing indirect measurements of the black hole's spin. The accretion process can vary dramatically depending on the rate at which material falls in. At low accretion rates, the disk may become radiatively inefficient, producing less light and more outflows. At high rates near or above the Eddington limit, where radiation pressure balances gravitational pull, the disk can become thick and turbulent, forming a luminous quasar. This diversity explains the wide range of black hole phenomena observed, from faint X-ray binaries to blazing active galactic nuclei. Even stellar mass black holes exhibit similar behavior on smaller scales. In binary systems where a black hole feeds on a companion star, the process produces X-ray emissions and sometimes small-scale jets, earning these systems the nickname microquasars. They follow the same physical principles as supermassive black holes, demonstrating that the underlying mechanics of accretion and jet formation are universal. One of the most spectacular examples of this interaction was captured in 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow in the galaxy M87, located about 55 million light-years away. The image revealed a bright ring of emissions surrounding a dark central region, consistent with light bending around a rotating black hole of about 6.5 billion solar masses. The bright ring represents the hot plasma of the accretion disk, while the dark center marks the shadow cast by the event horizon. Follow-up observations showed that M87's black hole also launches a powerful jet stretching for thousands of light-years, confirming that even at these unimaginable scales, black holes are not silent consumers but engines shaping their galaxies. These systems exemplify a kind of cosmic balance. Black holes, though defined by their ability to trap light, are also responsible for some of the brightest phenomena in existence. The very process of falling in, of matter surrendering to gravity, creates the energy that illuminates and sculpts the universe. In a sense, black holes demonstrate how nature transforms collapse into creation. The same forces that destroy structure on one scale generate complexity and order on another. By studying accretion disks and jets, astronomers not only learn how black holes behave, but also how galaxies live, grow, and eventually die. Black holes begin their lives as ordinary stars, but only the most massive ones end this way. The path from a bright, shining star to a collapsed remnant is dictated by a simple competition between two forces: gravity, which pulls inward, and pressure, which pushes outward. A star remains stable for most of its life because the outward pressure from nuclear fusion in its core perfectly balances gravity's inward pull. When that balance fails, the result can be catastrophic: a supernova explosion, and in some cases, the formation of a black hole. A typical star spends millions to billions of years fusing hydrogen into helium in its core. This process releases vast amounts of energy, keeping the star stable and luminous. When the hydrogen runs out, the core contracts and heats up, allowing new fusion reactions to begin. Helium into carbon, then carbon into oxygen, and so on, depending on the star's mass. Each new fuel source burns faster and provides less energy per unit mass. For stars like the Sun, this sequence ends gently, leaving behind a white dwarf. But for stars at least 20 to 25 times the Sun's mass, the story ends violently. As the core accumulates iron, fusion stops producing energy. Iron cannot be fused into heavier elements without consuming more energy than it releases. With no pressure to counteract gravity, the core collapses within a fraction of a second. The outer layers of the star rebound off the imploding core, generating a shock wave that tears the star apart in a supernova. The core's fate depends on its remaining mass. If it is between about 1.4 and 3 times the Sun's mass, it becomes a neutron star, an ultra-dense object made almost entirely of neutrons. If it exceeds that limit, known as the Tolman-Oppenheimer-Volkoff limit, nothing can stop the collapse. The core continues shrinking until it becomes a black hole. In a newly formed black hole, the mass is typically a few times that of the Sun, compressed into a region only a few kilometers across, roughly the size of a city. The gravitational pull near its surface is so strong that the escape velocity exceeds the speed of light. Any matter or radiation that ventures too close is trapped. These stellar black holes can form in isolation or as part of binary systems. When a black hole has a companion star, its gravity can pull gas from the companion, forming an accretion disk and producing strong X-ray emissions. These systems, known as X-ray binaries, were among the first indirect pieces of evidence for black holes. One of the best studied examples is Cygnus X1, discovered in the 1960s. It consists of a massive blue supergiant star and an invisible companion about 15 times the mass of the Sun. Observations of the star's orbit revealed that the companion must be a black hole. Binary systems also play a crucial role in the formation of black hole mergers. When two massive stars orbit each other closely, they can evolve together in ways that ensure their remnants eventually collide. As each star expands into a red supergiant, it may transfer material to its companion or even engulf it in a common envelope phase, spiraling closer together as they lose orbital energy. When both stars eventually collapse, they can leave behind a pair of black holes bound by gravity. Over millions or billions of years, they emit gravitational waves and slowly spiral inward until they merge, producing events like those detected by LIGO. Not all black holes form through supernova explosions. Some may arise through direct collapse, where a massive star's core collapses straight into a black hole without a visible explosion. In these cases, the outer layers fall inward rather than being ejected, making the process difficult to detect. Observations of massive stars that have disappeared from the sky without bright supernovae provide tentative evidence for this quiet formation pathway. The masses of stellar black holes vary widely, depending on the properties of their progenitor stars. In regions of low metallicity, where stars contain fewer heavy elements, stellar winds are weaker, allowing stars to retain more mass before collapsing. This leads to heavier black holes, sometimes reaching 50 to 80 solar masses or more. In contrast, metal-rich environments like the Milky Way tend to produce lighter black holes because their progenitor stars lose more material before death. At the upper end of the scale, there exists a theoretical gap between about 120 and 250 solar masses, where stars are thought to undergo pair instability supernovae. In such stars, intense gamma radiation in the core produces electron-positron pairs that reduce pressure, leading to runaway collapse and a complete explosion that leaves no remnant. Stars above that range, however, might collapse directly into massive black holes without such an explosion, potentially forming the seeds of supermassive black holes in the early universe. Over time, stellar black holes can grow by accreting matter or merging with others. In dense environments like globular clusters or galactic nuclei, repeated mergers could lead to intermediate mass black holes, ranging from hundreds to thousands of solar masses. Detecting these has proven difficult, but recent gravitational wave observations have hinted at their existence. The birth and growth of stellar black holes also influence the evolution of galaxies. Supernovae distribute heavy elements into space, enriching future generations of stars and planets. When those explosions instead collapse into black holes, they remove material from circulation. Over cosmic time, the ratio of black holes to stars reflects the history of star formation and the environments in which massive stars lived and died. In the modern universe, stellar black holes are relatively common. Estimates suggest there may be hundreds of millions of them scattered throughout the Milky Way alone, most completely invisible except when interacting with a companion or accreting gas. Each one is a fossil of a massive star that lived fast, burned brightly, and collapsed under its own weight, a compact record of stellar evolution in its most extreme form. Black holes come in several size classes, each defined by mass and by how they form. At the smallest end are stellar black holes, born from collapsing massive stars, typically between a few and a few dozen times the mass of the Sun. At the opposite extreme are supermassive black holes, weighing millions to billions of solar masses and residing at the centers of galaxies. Between these two groups lies a long hypothesized middle category, the intermediate mass black holes. Intermediate mass black holes, if they exist in large numbers, could represent the missing link in black hole evolution, objects heavy enough to bridge the gap between stellar remnants and galactic giants. Yet finding and confirming them has proven extraordinarily difficult. Their size makes them too massive to form from a single stellar collapse, but too light to anchor an entire galaxy. They also tend to emit little radiation unless something happens to feed them, leaving few observational traces. Evidence for intermediate black holes comes from several sources. In dense star clusters, astronomers have detected signs of unusually massive central objects, heavier than any known star, but far smaller than a supermassive black hole. For instance, the globular cluster 47 Tucanae in our galaxy shows stellar motions that suggest a central object of a few thousand solar masses. Similar clues appear in other clusters and dwarf galaxies. However, confirming these detections requires measuring how stars move at incredibly fine precision, often beyond the current limits of telescopes. Another line of evidence comes from rare, powerful X-ray sources, known as ultra-luminous X-ray sources, or ULXS. These objects shine brighter than any typical X-ray binary, but are fainter than full-blown quasars. One interpretation is that they host intermediate mass black holes accreting at moderate rates. In 2009, NASA's Hubble Space Telescope and Chandra X-ray Observatory detected such a source in the galaxy, ESO 243-49, suggesting a black hole with a mass of about 20,000 suns. Later observations of similar sources have strengthened the case that at least some ULXXS may indeed harbor mid-sized black holes. If intermediate black holes exist, how do they form? One possibility is through the merger of multiple stellar black holes in dense environments, such as globular clusters or the crowded cores of galaxies. Another is through the direct collapse of extremely massive stars in the early universe, or through the runaway growth of a single black hole consuming nearby material. Each pathway could produce objects in the 100 to 1,000 solar mass range. Supermassive black holes, by contrast, are a confirmed reality, even if their origins remain less clear. The one at the center of our Milky Way, known as Sagittarius A star, has about 4 million solar masses. It was detected through decades of careful measurements of stars orbiting an invisible point at incredible speeds. One such star, called S2, completes an orbit every 16 years at speeds up to 7,600 kilometers per second, about 4,700 miles per second. The only plausible explanation for this motion is a massive, compact object, a black hole, confined within a region smaller than our solar system. Supermassive black holes have been found in nearly every large galaxy observed, from the relatively quiet one in the Milky Way to the behemoths powering quasars billions of light years away. Their masses range from a few million to tens of billions of solar masses. The black hole in the galaxy Nikaia M87, famously imaged by the Event Horizon Telescope, weighs about 6.5 billion solar masses and drives a jet extending thousands of light years. How such colossal objects form remains one of the biggest open questions in astrophysics. Theories suggest two main possibilities. The first is hierarchical growth, where smaller black holes form from stars, gradually merge and accrete gas over cosmic time. The second is direct collapse, in which enormous clouds of primordial gas in the early universe collapse directly into black holes weighing thousands or hundreds of thousands of solar masses. These seed black holes could then grow quickly by accreting matter and merging with others to reach supermassive scales within a few 100 million years. Observations of extremely distant quasars, some dating to less than 1 billion years after the Big Bang, imply that at least some black holes must have formed and grown extraordinarily fast. The James Webb Space Telescope has detected galaxies hosting black holes that already weigh hundreds of millions of solar masses when the universe was less than 5% of its current age. This rapid growth challenges current models of star and galaxy formation, suggesting that black holes may have played a central role in shaping early cosmic structures. Once a supermassive black hole forms, it often becomes the gravitational anchor for an entire galaxy. Gas and dust drawn toward the center form stars more efficiently, and the black hole's gravity helps stabilize the galactic core. Yet the relationship between galaxies and their black holes is not one-sided. Observations show that the mass of a galaxy's central black hole correlates closely with the velocity and distribution of stars in the galactic bulge, a relationship known as the M-sigma relation. This suggests that the growth of a black hole and the evolution of its host galaxy are tightly linked, possibly through feedback from radiation and jets that regulate star formation. For instance, when a supermassive black hole is actively accreting material, the energy it releases can heat and drive out surrounding gas, preventing new stars from forming. This feedback mechanism may explain why large galaxies tend to stop forming stars earlier than smaller ones. Their central black holes effectively quench further growth. In this way, black holes, once thought to be purely destructive, actually shape the life cycle of galaxies. Supermassive black holes also merge, producing some of the universe's most violent events. When two galaxies collide and merge, their central black holes sink toward each other through a process called dynamical friction, eventually forming a binary pair. Over time, the pair emits gravitational waves and spirals inward until they coalesce into a single, more massive black hole. These mergers not only release immense gravitational energy, but also may produce observable signatures, such as displaced black holes. Between the smallest stellar black holes and the titanic supermassive ones lies a mysterious middle ground, the realm of intermediate mass black holes, or IMBHS. These objects are thought to range from roughly 100 to several 100,000 times the mass of the Sun, bridging the gap between stellar collapse remnants and the colossal engines at galactic centers. Yet despite decades of searching, they have proven extraordinarily difficult to confirm. Detecting black holes of any size relies on their effects on nearby matter or on light passing through their gravitational field. For stellar black holes and binaries, we can infer their presence by the motion of a companion star or by the radiation from an accretion disk. For supermassive black holes, the motions of entire star clusters and gas clouds in galactic centers reveal their enormous gravitational pull. Intermediate black holes, however, occupy an awkward middle scale, too massive to form in ordinary stellar systems, yet too small to dominate entire galaxies. They can exist quietly in the outskirts of galaxies or within dense star clusters, leaving few obvious signs. The first hints of IMBHS came from ultraluminous X-ray sources, ULXS. These are points of intense X-ray emission found outside galactic centers, often brighter than any stellar binary system, but dimmer than active galactic nuclei. Their luminosities suggest accretion onto black holes with masses in the intermediate range. One notable example is HLX-1 in the galaxy ESO 243-49, whose X-ray output implies a black hole of about 20,000 solar masses. Another candidate, M82X1, appears to harbor a black hole around 400 times the Sun's mass. Gravitational wave detections have also provided indirect evidence for intermediate mass black holes. Some mergers observed by LIGO and Virgo involve remnants that are too massive to be explained by ordinary stellar evolution. For instance, GW190521, detected in 2019, resulted from the merger of two black holes of roughly 85 and 66 solar masses, producing a final black hole of about 142 solar masses, the first confirmed object squarely in the intermediate range. Events like this suggest that successive mergers in dense clusters may gradually build up larger black holes. Globular clusters are prime environments for such processes. These dense collections of ancient stars, often found in the halos of galaxies, contain conditions where stellar black holes can sink toward the center, merge, and form heavier remnants. Some globular clusters show kinematic evidence for a massive dark object at their core, consistent with an intermediate black hole. However, such detections remain tentative, as other effects, like the combined gravity of many stars, can mimic the same motion patterns. If intermediate black holes exist, they could play a key role in cosmic evolution. They may have served as the building blocks for the supermassive black holes that now reside in galactic centers. In the early universe, frequent mergers and rapid gas accretion could have allowed IMBHs to grow into the billion solar mass monsters that power quasars. Understanding how these intermediate objects form and evolve is essential for filling the gap between stellar death and galactic structure. Supermassive black holes, SMBHs, on the other hand, are well established, even if their origins remain mysterious. Nearly every large galaxy, including our own Milky Way, contains one at its core. These giants range from a few million to tens of billions of solar masses. Despite their size, they occupy surprisingly compact volumes. The event horizon of the Milky Way's black hole, Sagittarius A star, is about 24 million kilometers across, roughly 15 million miles, which is only about the size of Mercury's orbit around the Sun. The presence of Sagittarius, a star, was confirmed through decades of precise observations of stars orbiting the galactic center. Astronomers tracked the motion of a star known as S2, which completes a full orbit every 16 years at speeds exceeding 7,600 kilometers per second, around 4,700 miles per second. The star's path revealed an invisible object with a mass of about 4 million suns, confined to a region smaller than our solar system. No known object other than a black hole could account for such density, the event. Horizon Telescope's 2022 image of Sagittarius, a star, provided further confirmation. Although blurrier than the earlier M87 image, due to the smaller scale and more rapid variability, it showed the same basic structure, a glowing ring of hot plasma surrounding a dark shadow. The agreement between the observed shadow size and theoretical predictions from general relativity was striking, further validating Einstein's theory in one of the most extreme gravitational fields known. Supermassive black holes are not merely passive occupants of galactic centers. Their influence extends far beyond their immediate surroundings. Through jets, winds, and radiation from accretion disks, they regulate the growth of their host galaxies. This relationship is reflected in a tight correlation between a galaxy's central black hole mass and the velocity dispersion of its stars, a link known as the M-sigma relation. It suggests that galaxies and their central black holes grow together, influencing each other's evolution. The exact mechanism of this coevolution remains under study. One possibility is feedback. As the black hole accretes gas, it emits energy that heats or expels the surrounding medium, limiting further star formation and black hole growth. Over time, this self-regulating cycle produces the observed balance between galactic mass and central black hole size. Some galaxies, like M87, display black holes of staggering proportions. The M87 black hole's mass, about 6.5 billion suns, gives it an event horizon roughly 20 billion kilometers wide, or about 12 billion miles. Yet even this is dwarfed by the current record holder, TON 618, estimated at 66 billion solar masses. Its event horizon would extend nearly 400 billion kilometers, around 250 billion miles, more than 60 times the distance from the Sun to Pluto. Objects of that scale defy easy imagination. They are gravitational engines shaping entire cosmic structures. Despite their enormity, supermassive black holes are not always active. Most galaxies host quiet central black holes that accrete little material and emit only faint radio or X-ray signals. These dormant giants can awaken when fresh gas is supplied, perhaps through a galactic merger or tidal disruption of a passing star, and flare up as quasars or active galactic nuclei. Over. Cosmic history. The number of such luminous AGN has declined dramatically as galaxies have stabilized and gas supplies have dwindled. Both intermediate and supermassive black holes illustrate a core truth of astrophysics. Nature builds complexity through scale. The same physical laws govern the collapse of a dying star and the feeding of a quasar. Only the mass and environment change the expression. Across the universe, from tiny stellar remnants to billion solar mass giants, black holes operate under the same fundamental principles: gravity, rotation, and the interplay between energy and space-time. Detecting a black hole is an indirect process by necessity. Since no light or matter escapes from within the event horizon, astronomers must infer a black hole's presence by observing its effects on the surrounding environment. Over the past century, a wide range of techniques have been developed to detect, study, and even image black holes, from X-ray emissions and radio waves to gravitational lensing and gravitational waves. The earliest clues came from stellar motions that could not be explained by visible companions. In binary systems, for example, one star might orbit an unseen partner with such speed and regularity that the missing mass could be estimated. If the invisible companion exceeded about 3 solar masses, it could not be a neutron star or white dwarf, leaving a black hole as the only plausible explanation. This reasoning identified some of the first black hole candidates in the 1960s and 70s, including Cygnus X1, which remains one of the best studied examples. X-ray astronomy revolutionized this field. When matter falls toward a black hole, it does not simply disappear. Instead, it spirals inward, forming an accretion disk, a hot, dense structure where friction and compression heat the gas to millions of degrees. These temperatures cause the disk to emit X-rays, which can be detected by space-based observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton. The pattern and variability of X-ray emissions reveal details about the disk's structure, the black hole's mass, and even its spin. Variations in X-ray brightness can occur on timescales of milliseconds to hours, depending on the size of the inner disk. Because the fastest changes must originate from the smallest regions, the timing data helps set limits on the black hole's radius. By combining X-ray spectra and timing information, astronomers can estimate how close material is orbiting to the event horizon and whether the black hole is rotating rapidly or slowly. Radio astronomy offers another powerful tool. Some black holes, especially supermassive ones, produce relativistic jets, narrow beams of plasma that shoot out from their poles at speeds close to that of light. These jets emit strong radio waves that can travel vast distances through space. By studying their structure, astronomers can learn about the black hole's magnetic fields and how energy is extracted from its rotation. The Event Horizon Telescope, EHT, uses a global network of radio dishes operating in synchrony, creating a virtual telescope the size of Earth. This is what allowed the historic imaging of the black holes in M87 and Sagittarius A star. Gravitational lensing provides a more subtle but equally revealing signature. According to general relativity, a massive object bends the path of light passing nearby. When a black hole lies between us and a distant star or galaxy, it can distort and magnify the background light, acting like a natural cosmic lens. These events, known as microlensing, can temporarily brighten a star's light, revealing the mass of the unseen lensing object. In rare cases, precise lensing measurements may even detect isolated black holes wandering between stars. The Hubble Space Telescope and now the James Webb Space Telescope, JWST, have contributed by observing the central regions of galaxies with high resolution. By measuring how stars and gas clouds move under the influence of gravity, astronomers can infer the mass distribution and identify supermassive black holes. For example, Hubble observations of galaxy NGC 4261 showed a rapidly rotating disk of gas in its nucleus, consistent with a 1.2 billion solar mass black hole. Gravitational waves have added an entirely new observational window. Detected for the first time in 2015, these ripples in space-time occur when two massive objects, such as black holes or neutron stars, orbit each other and eventually merge. Instruments like LIGO, Virgo, and CAGRA can measure these minute distortions in space-time, smaller than a proton's width, caused by passing gravitational waves. Each detection provides detailed information about the masses, spins, and distances of the merging black holes. The gravitational wave signal follows a distinctive pattern, a rising chirp in frequency and amplitude as the two black holes spiral together, followed by a brief burst as they merge and a fading ring down as the final remnant settles into equilibrium. These observations have not only confirmed the existence of binary black hole systems, but also provided population data, revealing that black holes are more common and more diverse than once thought. Multi-messenger astronomy, the combination of gravitational waves, electromagnetic radiation, and sometimes neutrinos, has become the new frontier. When two neutron stars merged in 2017, GW170817, both gravitational and light signals were detected, allowing scientists to study the event from multiple perspectives. A similar detection for black hole mergers remains a goal, though such events are less likely to emit visible or gamma-ray light unless gas is present. Another detection method involves stellar dynamics near galactic centers. By precisely tracking the orbits of stars close to a suspected black hole, astronomers can deduce the central mass. This technique was key in confirming Sagittarius A star. Infrared telescopes, such as the Very Large Telescope, VLT in Chile, and the Keck Observatory in Hawaii, track the positions and velocities of stars that pass within light days of the Milky Way's center, offering a direct test of general relativity under extreme conditions. Advanced modeling and computer simulations also play a major role. By simulating accretion disks and relativistic jets, astrophysicists can predict the electromagnetic spectrum, polarization, and time variability expected from different configurations. Comparing these models with actual observations helps constrain the spin and orientation of black holes and the geometry of surrounding matter. Even indirect statistical studies can reveal black hole populations. For example, surveys of X-ray binaries, microlensing events, and gravitational wave detections allow scientists to estimate how many black holes exist in a given galaxy. The current best estimate for the Milky Way suggests at least 100 million stellar mass black holes, though only a tiny fraction have been identified. Together, these techniques have transformed black holes from theoretical curiosities into well-studied astrophysical objects. Each detection method offers a different perspective, from the flickering light of an accretion disk to the faint tremor of space-time itself. The more we observe, the clearer the picture becomes. Black holes are not rare anomalies, but fundamental components of the universe, shaping galaxies, generating radiation, and testing the limits of physics. The region near the event horizon of a black hole is a natural laboratory for extreme physics. Here, the laws of nature operate at their most intense limits. Gravity curves space-time so severely that even light must bend inward. Matter is accelerated to a significant fraction of the speed of light. Temperatures soar into the billions of degrees, and time itself behaves in ways that defy common sense. When gas or dust approaches a black hole, it rarely falls straight in. Instead, it carries angular momentum, a kind of rotational inertia, that prevents direct infall. This leads to the formation of an accretion disk, a flattened, swirling structure made of plasma orbiting the black hole. Friction and magnetic turbulence within the disk cause inner layers to spiral inward while outer layers move outward, dissipating energy in the process. This process converts gravitational potential energy into heat and radiation with astonishing efficiency. In the most active systems, such as quasars, as much as 10% of the infalling matter's rest mass can be converted into radiation. By comparison, nuclear fusion in stars converts only about 0.7%. This means that, gram for gram, accretion onto a black hole is the most efficient energy source known in the universe. For example, if 1 kilogram of matter, 2.2 pounds, were accreted onto a black hole, it could release energy equivalent to about 90 trillion joules, roughly the same as the explosive energy of 20 kilotons of TNT, the yield of the Hiroshima bomb. The disk's inner edge lies close to the innermost stable circular orbit, ISCO, the smallest orbit where matter can still revolve without plunging inward. For a non-rotating black hole, the ISCO is 3 times the Schwarzschild radius, but for a maximally spinning black hole, it can shrink to as little as half that distance. The closer the ISCO, the hotter and brighter the disk becomes, since matter releases more energy before crossing the event horizon. Temperatures in the inner accretion disk can exceed 100 million Kelvin, around 180 million Fahrenheit. At these temperatures, atoms are completely ionized, and the disk emits primarily X-rays and gamma rays. The pattern of these emissions depends strongly on the black hole's mass and spin. Supermassive black holes have cooler disks peaking in ultraviolet light, while stellar mass black holes radiate mostly in X-rays. Magnetic fields twisted by the rotation of the disk and black hole can launch relativistic jets, narrow beams of charged particles ejected perpendicular to the disk. The exact mechanism remains an area of research, but the leading explanation is the Blandford-Znaeck process, where rotational energy from the black hole is extracted through magnetic field lines anchored in the accretion disk. These jets can stretch for thousands of light years and carry enormous energy, affecting the intergalactic environment far beyond the black hole's immediate vicinity. Close to the event horizon, relativity dominates every aspect of motion and perception. To a distant observer, an object falling toward the black hole appears to slow down, its clock ticking ever more slowly due to gravitational time dilation. Light emitted by the object is increasingly redshifted, stretched to longer wavelengths until it fades completely. To the falling object, however, time proceeds normally, and it crosses the event horizon in a finite interval without noticing any physical boundary. This distinction between the external and internal perspectives is one of the most striking consequences of general relativity. The event horizon is not a material surface, but a causal boundary, a region beyond which signals cannot return. To the outside universe, infalling matter seems to freeze and fade, never quite disappearing, but in its own frame of reference, it continues inward toward the singularity, where density and curvature reach theoretical infinity. Radiation from the accretion disk does not come from within the event horizon, but from just outside it. In this region, light follows distorted paths, wrapping around the black hole multiple times before escaping. The result is the characteristic photon ring observed by the Event Horizon Telescope, a bright circular band surrounding a dark shadow. This structure is a direct consequence of the extreme warping of space-time near the horizon. The gravitational field also affects the path of light from background sources. If a star or galaxy lies behind the black hole, its image can be distorted or even multiplied, forming rings or arcs. The strongest such lensing effects occur when viewing a bright source directly behind a massive black hole, producing what is called an Einstein ring. Another relativistic phenomenon near black holes is frame dragging. In general relativity, a rotating mass drags space-time itself around with it, an effect known as the lens-Thirring effect. Near a rapidly spinning black hole, this effect becomes extreme. Any object or bit of plasma must rotate in the same direction as the black hole within a region known as the ergosphere. Inside the ergosphere, it is theoretically possible to extract energy from the black hole's rotation, as predicted by the Penrose process, where a particle entering the ergosphere splits, sending one fragment into the black hole while the other escapes with greater energy than it had before. From the perspective of physics, the environment around a black hole represents a test of both general relativity and quantum mechanics. The two theories work with extraordinary accuracy in their respective domains, yet near the event horizon, especially near the singularity, their predictions diverge. General relativity predicts infinite density and curvature, while quantum theory forbids such infinities. Reconciling these two frameworks is one of the great unresolved challenges of modern science. In short, the region near a black hole is where the universe bends its own rules. Gravity, light, time, and matter behave in ways that stretch human intuition. These environments are not theoretical abstractions, but real observable systems, dynamic, luminous, and violent. They show us what happens when nature operates at full intensity, where the boundaries between classical and quantum, between possible and impossible, begin to blur. Inside the event horizon, the usual laws of physics lose their predictive power. Once matter crosses this invisible boundary, it can no longer send information outward. The path of every particle and photon bends inexorably toward the singularity at the center. To describe what happens there requires a theory that unites general relativity, which governs the large-scale curvature of space-time, with quantum mechanics, which governs the behavior of particles at the smallest scales. At present, no such unified theory exists in complete form. According to classical general relativity, all matter and energy falling into a black hole collapse into a singularity, a point of zero volume and infinite density where the curvature of space-time becomes infinite. In such a scenario, the known equations break down entirely. The singularity marks a boundary not just in space, but in knowledge itself. It is a place where prediction becomes impossible, and where the concept of space and time may cease to have meaning. Most physicists believe that this infinite density is not physical, but instead reflects the limitations of general relativity. Quantum mechanics should, in principle, smooth out these infinities. A leading idea is that, instead of a true singularity, the core of a black hole may consist of an extremely dense but finite region of space-time, perhaps a Planck-scale structure, where gravity becomes quantized. The Planck length, about 1.6 times 10 to the negative 35th meters, roughly 10 to the negative 34th inches, is the smallest scale at which space-time can meaningfully be described. At this level, space may no longer be continuous, but composed of discrete units, somewhat like pixels in an image. Several theories attempt to describe this regime. Loop quantum gravity proposes that space itself is woven from tiny loops, forming a kind of quantum fabric. In this view, the singularity might be replaced by a bounce, where collapsing matter rebounds into a new region of space-time, possibly giving rise to a new universe. Other approaches, like string theory, describe all matter and forces as manifestations of one-dimensional, vibrating strings. Within that framework, black hole cores might correspond to highly compact states known as fuzzballs, where the traditional event horizon is replaced by a tangled surface of strings and brains, eliminating the singularity entirely. Despite these theoretical efforts, the interior of a black hole remains hidden behind the event horizon, inaccessible to observation. Even if a spacecraft could somehow survive the gravitational forces outside the horizon, once it crossed that threshold, it could never transmit data back. Thus, our understanding of black hole interiors relies entirely on extrapolation from physical theory. For an observer falling into a supermassive black hole, the experience would differ from what popular depictions often suggest. In smaller black holes, the tidal forces, differences in gravitational pull between one end of the body and the other, would become lethal long before reaching the horizon, stretching and compressing the object in an effect colloquially called spaghettification. Near a supermassive black hole, however, the curvature of space-time at the horizon is gentler. An astronaut crossing it might not feel any immediate change, even as the outside universe appears to speed up and fade away. Inside, however, all possible trajectories still lead toward the center. There is no way to resist the inward pull, and within a short, proper time, perhaps seconds or minutes, the traveler would encounter conditions where the curvature becomes extreme. The distinction between space and time would blur. Directions that once led forward in time might now point inward toward the singularity. Some speculative models suggest that information might not be truly lost. One possibility is that quantum effects cause the black hole's horizon to behave like a membrane, storing information in microscopic fluctuations. This idea aligns with the holographic principle, which proposes that all the information contained within a volume of space can be encoded on its boundary surface. In that view, the three-dimensional contents of a black hole could be represented on its two-dimensional event horizon, like a cosmic projection. If this principle is correct, the interior of a black hole may not be a separate region of space at all, but rather a different way of encoding information that remains accessible in principle through quantum processes. These ideas remain speculative, but form the foundation of ongoing efforts to reconcile quantum theory and general relativity. Ultimately, the singularity problem points to the need for a theory of quantum gravity, a framework that can describe both the continuous curvature of space-time and the discrete probabilistic nature of quantum fields. Experiments cannot yet probe such extreme conditions, but progress continues through indirect means, such as studying black hole thermodynamics and Hawking radiation, which connects gravity, quantum mechanics, and entropy in unexpected ways. In 1974, Stephen Hawking made a discovery that transformed our understanding of black holes from eternal absorbers to dynamic, evolving objects. Using the principles of quantum field theory and curved spacetime, he demonstrated that black holes are not perfectly black. Instead, they emit a faint thermal radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, implies that black holes can gradually lose mass and eventually evaporate completely. To understand this, it helps to recall that the vacuum of space is not truly empty. According to quantum mechanics, it constantly seethes with fluctuations, brief appearances of virtual, particle pairs consisting of a particle and its antiparticle. These pairs normally annihilate almost immediately, returning their borrowed energy to the vacuum in accordance with the uncertainty principle. However, near the event horizon of a black hole, the extreme curvature of spacetime can separate these pairs before they recombine. If one member of the pair falls into the black hole while the other escapes, the escaping particle becomes real, carrying away energy. From the outside, it appears as if the black hole has emitted a particle. To conserve energy, the black hole must lose an equivalent amount of mass. Over time, this leads to a slow leakage of energy, a gradual evaporation process. The spectrum of Hawking radiation is thermal, meaning it resembles that of a hot body emitting black body radiation. The temperature of this radiation, known as the Hawking temperature, depends inversely on the black hole's mass. The smaller the black hole, the hotter it becomes. For a stellar mass black hole of about 10 solar masses, the temperature is roughly 60 nanokelvin, or 60 billionths of a degree above absolute 00, far colder than the cosmic microwave background radiation. Such black holes gain energy from their environment faster than they lose it, so their evaporation is negligible. For much smaller black holes, the situation changes dramatically. A black hole with the mass of a mountain, about 10 to the 11th kilograms, or roughly 100 billion tons, would have a temperature near 10 to the 12th Kelvin. around 1.8 trillion degrees Fahrenheit. It would emit a powerful flux of gamma rays and subatomic particles, evaporating rapidly. The smaller it becomes, the faster the process accelerates, ending in an explosive final burst of radiation. This leads to the intriguing idea of primordial black holes, hypothetical remnants formed in the early universe from regions of high density. If they existed with masses below about 10 to the power of 12 kilograms, many would have already evaporated by now, possibly contributing to high-energy cosmic rays. Searches for their gamma-ray signatures have so far yielded no confirmed detections, but the concept remains a testable frontier in cosmology. Hawking's result carries profound implications for physics. It connects three previously distinct fields: general relativity, which describes gravity and space-time; quantum mechanics, which governs subatomic particles; and thermodynamics, which deals with energy, entropy, and temperature. This connection revealed that black holes have a measurable entropy, proportional to the area of their event horizon rather than their volume. This is known as the Bekenstein-Hawking entropy. The concept that entropy scales with area rather than volume is central to the holographic principle, which suggests that the information content of a region of space can be represented by data encoded on its boundary. This insight bridges quantum mechanics, thermodynamics, and geometry in ways that continue to shape modern theoretical physics. However, Hawking's discovery also led to one of the deepest puzzles in science: the black hole information paradox. If a black hole can evaporate completely, what happens to the information about the matter that fell into it? Quantum mechanics insists that information cannot be destroyed. It may be scrambled, but never lost. Yet in Hawking's original model, the radiation emitted by a black hole is purely thermal, containing no information about what formed the black hole or what entered it. This apparent loss of information would violate one of the core principles of quantum theory. Over the past decades, physicists have proposed numerous possible resolutions. Some argue that information is encoded in subtle correlations within the Hawking radiation itself, meaning the radiation is not perfectly thermal. Others suggest that quantum gravity effects might preserve information at the horizon in a way consistent with the holographic principle. More radical proposals involve the idea that the information could escape through quantum tunneling, or that the end state of evaporation is not complete disappearance, but a stable Planck mass remnant storing the information. Recent developments in string theory and quantum gravity research support the idea that information is preserved. Theoretical work on ADS/CFT correspondence, a framework where gravity in a higher dimensional space is equivalent to a quantum field theory on its lower dimensional boundary, provides mathematical examples of how black hole evaporation can occur without information loss. Still, a full, universally accepted solution remains elusive. Hawking himself later revised his position, suggesting that information might indeed escape in a highly scrambled form. In 2004, he presented a new argument that black hole radiation could carry subtle correlations, meaning the information was not truly destroyed, but transformed beyond easy recognition. This represented a partial reconciliation between quantum mechanics and general relativity, though the exact mechanism remains unknown. In the far future, when the universe has cooled and galaxies have faded, black hole evaporation may become the dominant source of radiation. The last whispers of energy from the final evaporating black holes would mark the closing act of a thermodynamic universe, returning even the most powerful gravitational wells to the vacuum from which they arose. The black hole information paradox remains one of the deepest unsolved problems in modern physics. It arises from a direct conflict between the predictions of general relativity and the fundamental principles of quantum mechanics. General relativity, when taken at face value, implies that any information entering a black hole is lost to the universe forever. Quantum mechanics, on the other hand, insists that the evolution of physical systems must be unitary, meaning information cannot be destroyed, only transformed. The paradox, first clearly articulated by Stephen Hawking in the 1970s, forced physicists to reconsider the nature of space, time, and reality itself. The paradox can be summarized in a simple thought experiment. Imagine a black hole forming from the collapse of a star. Over time, according to Hawking's theory, the black hole radiates away its mass in the form of thermal Hawking radiation until it eventually evaporates completely. If that radiation is purely thermal, containing no information about what fell in, then the detailed state of the original matter is lost forever. This outcome violates quantum theory, which requires that information about a system's initial state can always, at least in principle, be recovered from its final state. Physicists have spent decades proposing possible resolutions to this contradiction. The first category of ideas involves the possibility that Hawking radiation is not exactly thermal. In quantum mechanics, even processes that appear random can contain hidden correlations. If the outgoing radiation encodes information in subtle quantum entanglements, then, in principle, the information could be preserved, though hopelessly scrambled. This view treats the black hole as a kind of ultimate information processor, or scrambler. One of the earliest theoretical frameworks to address this was the holographic principle, developed in the 1990s by Gerard 't Hooft and Leonard Susskind. Inspired by the work of Jacob Bekenstein on black hole entropy, they proposed that the information content of all the matter and energy inside a region of space can be represented by data encoded on its boundary surface, like a hologram, where a three-dimensional image emerges from a two-dimensional pattern. In this model, the information about everything that falls into a black hole could be stored on the event horizon itself, in microscopic degrees of freedom that evolve according to quantum laws. This idea found mathematical support in string theory, particularly through the ADS/CFT correspondence formulated by Juan Maldacena in 1997. In this framework, a gravitational theory in a higher dimensional bulk space, anti-de Sitter space, or ADS, is equivalent to a quantum field theory without gravity on its lower dimensional boundary, a conformal field theory, or CFT. This duality provides explicit examples where black hole-like objects evolve unitarily, meaning information is preserved, even though it appears to be hidden behind a horizon. The ADS/CFT correspondence effectively resolved the information paradox within the context of those specific models. It showed that in a universe governed by such a duality, black hole evaporation would not destroy information. Instead, the information would be encoded in extremely complex correlations among the emitted particles. Although our own universe is not anti-de Sitter space, the success of this correspondence provides strong evidence that unitarity should be preserved in any consistent theory of quantum gravity. However, another challenge emerged in the 2000s, the firewall paradox. This problem arose from attempts to make the information-preserving picture mathematically consistent. In 2012, physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, showed that if information escapes through Hawking radiation while maintaining quantum entanglement with the black hole interior, it leads to a violation of another principle of relativity, the equivalence principle, which states that a freely falling observer should not experience anything unusual when crossing the event horizon. According to the AMPS argument, these three statements cannot all be true at once. 1. Information is preserved, unitarity. 2. Quantum field theory holds near the horizon, no exotic new physics. 3. The equivalence principle holds, no violent experience at the horizon. At least one must give way. If the first two remain true, the event horizon cannot be smooth. Instead, an infalling observer would encounter a searing wall of high-energy particles, a firewall, that burns everything instantly upon crossing. This idea shocked the physics community because it contradicted decades of accepted understanding that nothing special happens at the event horizon. Many researchers reject the firewall hypothesis, seeing it as a sign that our understanding of quantum entanglement in curved space-time is incomplete. Alternatives include the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. This idea suggests that entangled particles' EPR pairs might be connected by non-traversable wormholes, Einstein-Rosen bridges, or ER. In this view, the entanglement between particles inside and outside the black hole could correspond to microscopic wormholes linking the two regions, preserving information without violating the equivalence principle. Though speculative, ER equals EPR hints at a deep geometric interpretation of quantum entanglement. Another line of reasoning focuses on the concept of quantum extremal surfaces and the Page curve. Don Page, a student of Hawking's, predicted that if information is preserved, the entropy of Hawking radiation should follow a specific time-dependent pattern. It should increase initially as radiation is emitted, then decrease later as the black hole shrinks and information begins to leak out. Recent advances in quantum gravity calculations have reproduced this Page curve using holographic techniques, providing strong theoretical evidence that information does, in fact, escape gradually in a consistent way. Still, the precise microscopic mechanism remains unknown. Whether information is stored in correlations at the horizon, encoded in the radiation itself, or preserved through deep space-time connectivity, no experiment can yet distinguish among these possibilities. The paradox has evolved from a question about black holes to a question about the foundations of physics. How do space, time, and information relate at the most fundamental level? The broader implication is that information may be the true currency of reality. Black holes, once seen as cosmic destroyers, might instead be nature's most efficient data compressors, objects that test the ultimate limits of how information can be stored, processed, and retrieved in a universe governed by quantum laws. The connection between wormholes, black holes, and quantum entanglement represents one of the most imaginative and consequential areas of modern theoretical physics. It's an attempt to merge two seemingly unrelated aspects of nature, the geometry of space-time and the non-local correlations that define quantum mechanics. A wormhole, or Einstein-Rosen bridge, is a hypothetical tunnel-like structure connecting two separate regions of space-time. First proposed in 1935 by Albert Einstein and Nathan Rosen, it emerged from the mathematics of general relativity. They discovered that the equations describing a Schwarzschild black hole could be extended to reveal two asymptotically flat universes joined at a common throat. In theory, such a structure could serve as a shortcut through space-time, a bridge between distant locations, or even between entirely different universes. However, the original Einstein-Rosen bridge is not traversable. It collapses faster than any signal or particle could cross it. For practical purposes, it's a mathematical curiosity rather than a cosmic tunnel. Later work, including that of Kip Thorne and Michael Morris in the late 1980s, examined whether traversable wormholes could exist if exotic matter with negative energy density were present to hold the throat open. Quantum effects, such as the Casimir force, show that negative energy is possible in small amounts, but sustaining it at macroscopic scales remains beyond known physics. The intriguing connection between wormholes and entanglement, summarized in the phrase ER equals EPR, was proposed by Juan Maldacena and Leonard Susskind in 2013. The ER refers to Einstein-Rosen bridges, while EPR refers to the Einstein-Podolsky-Rosen paradox of quantum entanglement. Their conjecture suggests that entangled particles are connected by non-traversable wormholes at the quantum level. These wormholes are not physical tunnels one could travel through, but geometric representations of entanglement itself. In this view, space-time connectivity and quantum entanglement may be two sides of the same coin. Entangled systems share information instantaneously, regardless of distance, without violating relativity, because no usable signal travels faster than light. If each pair of entangled particles is linked by a microscopic wormhole, the fabric of space-time could literally be woven from entanglement. This perspective offers a conceptual bridge between quantum mechanics and general relativity, suggesting that geometry and information are fundamentally intertwined. Recent theoretical models have explored traversable wormholes in more detail, especially within the context of quantum gravity and holography. In 2017, researchers Daniel Jafferis, Ping Gao, and Aaron Wall showed that certain quantum effects, specifically negative energy generated by quantum entanglement, could make a wormhole traversable without violating causality. Their model, based on the ADS/CFT correspondence, describes how information or particles could travel between two entangled black holes connected by a wormhole-like geometry. While this remains entirely theoretical, it suggests that quantum entanglement can mimic the effects of a physical bridge through space-time. A pair of maximally entangled black holes could, in principle, behave as two mouths of the same wormhole. If one black hole is disturbed, the effects could be reflected in the other, as though they were linked through a hidden channel. This connection doesn't permit faster-than-light travel, but it reshapes how physicists think about distance and locality. Computer simulations of quantum systems, especially using tools from quantum information theory, have begun to reproduce simplified versions of this phenomenon. In 2022, researchers at Google's Quantum AI Lab performed an experiment using a small quantum processor to simulate the dynamics of a traversable wormhole in a toy model. They encoded information into a system described by a dual holographic theory and observed behavior consistent with information passing through a wormhole-like channel. The result didn't create a real wormhole, but it demonstrated how entanglement and space-time geometry can be mathematically equivalent under certain conditions. The link between wormholes and information transmission also offers potential insight into the black hole information paradox. If entangled pairs of particles, those that form as Hawking radiation, are connected by microscopic wormholes to the black hole interior, then information could, in principle, leak out in a consistent way. This would resolve the paradox by preserving unitarity. The information never truly disappears, but is encoded non-locally in the structure of space-time itself. In that sense, a black hole might not be a one-way trap, but part of a complex quantum network, constantly exchanging information with the outside universe. The geometry of space-time and the logic of entanglement could together define how information is stored and transmitted, even in regions beyond classical understanding. At present, wormholes remain speculative. No empirical evidence supports their existence, and most models require conditions far beyond anything achievable or observable. But the mathematics connecting them to quantum entanglement continues to deepen. It suggests that the fundamental fabric of the universe may be built not from particles or fields, but from relationships, from the correlations that bind distant regions into a coherent whole. Black holes, particularly the supermassive variety, play a central role in the structure and evolution of galaxies. Far from being isolated gravitational traps, they are deeply intertwined with their cosmic environments. The interplay between a black hole and its host galaxy is a two-way relationship, each influencing the growth, dynamics, and long-term fate of the other. At the heart of nearly every large galaxy lies a supermassive black hole, with masses ranging from a few million to tens of billions of times that of the Sun. The discovery of these central giants reshaped the field of galactic astronomy. Observations have shown that the mass of a galaxy's central black hole correlates closely with properties of the surrounding stellar bulge, particularly the velocity dispersion of its stars. This correlation, known as the M-sigma relation, suggests that galaxies and their black holes evolve together. The mechanism driving this coevolution is feedback, the process by which a growing black hole affects the gas and stars around it. As matter spirals into the black hole through an accretion disk, it releases enormous amounts of energy in the form of radiation, winds, and jets. This energy doesn't simply vanish into space, it interacts with the surrounding interstellar medium, heating and dispersing it. The result is that black holes can regulate the very process of star formation in their host galaxies. In young, gas-rich galaxies, rapid black hole growth produces quasars, the brightest objects in the universe. A quasar's luminosity can outshine the combined light of all the stars in its host galaxy. The power source is the accretion disk, where infalling material releases gravitational energy as light across the electromagnetic spectrum. Temperatures near the inner disk can reach tens of millions of degrees, producing intense ultraviolet and X-ray radiation. The radiation and outflows from these active galactic nuclei, AGN, can drive vast galactic winds, capable of expelling gas from the galaxy's core. When this happens, the galaxy's ability to form new stars diminishes, effectively quenching its growth. Observations show that galaxies with active nuclei often have reduced star formation rates compared to quieter ones of similar size. This feedback process is one reason why massive galaxies today are dominated by old, red stars rather than new, blue ones. Jets launched from black hole accretion disks add another layer to this interaction. These relativistic jets can extend for thousands of light years, plowing into intergalactic space and inflating giant lobes of radio-emitting plasma. The jets carry enormous mechanical energy, which can heat the gas in galaxy clusters and prevent it from cooling and condensing into new stars. This maintenance mode, feedback, is essential for explaining the observed balance between hot gas and star formation in massive galaxies. An example of such large-scale influence can be seen in the galaxy M87, whose supermassive black hole, imaged by the Event Horizon Telescope, powers a jet that stretches more than 5,000 light-years. The energy output of that jet, equivalent to hundreds of supernovae per year, stirs and stabilizes the surrounding intergalactic medium. Similar effects are observed in clusters like Perseus, where cavities or bubbles in the hot gas coincide with radio lobes from central black holes. These structures show that black holes play a crucial role in the thermal balance of entire galaxy clusters. The growth of supermassive black holes themselves is driven by cosmic history. In the early universe, gas was abundant, and mergers between young galaxies were frequent. These events funneled vast quantities of matter toward galactic centers, triggering both starbursts and quasar activity. Quasars peaked in number roughly 10 billion years ago, during a period known as cosmic noon, when black holes and galaxies grew most rapidly. Since then, as the universe has expanded and gas supplies have dwindled, quasar activity has declined sharply. Not all black holes are equally active, however. Many supermassive black holes today are quiescent, accreting only trace amounts of material. Sagittarius, a star at the center of the Milky Way, is one example. It emits only a faint radio glow, consuming perhaps a few billionths of a solar mass per year. Yet evidence suggests it was far more active in the past. X-ray echoes observed in nearby gas clouds indicate that a few centuries ago, Sagittarius A star briefly flared with luminosity comparable to a low-level AGN. This episodic behavior appears to be typical. Black hole activity cycles on timescales of thousands to millions of years, depending on the availability of gas. Some galaxies show relics of past activity, ionized gas clouds or radio structures, long after the central engine has faded. These signs reveal that black hole feedback operates in bursts, shaping galaxies in fits and starts rather than in a steady flow.